Okay, Mr. Nagy's Physics 11 class, looking at waves still, and this is our second video on waves. Our first one kind of an introduction, some parts of the wave. So just to review here, where we stood at the end of all that, from our introductory video and from our activity out in the hall where we stretched sprinkies and sprinkies, how about slinkies, out there, and we sent some waves. We created longitudinal waves and transverse waves with our slinky. We could move our slinky side to side as well as moving it that way. When we moved it side to side, we created a transverse wave, and the wave kind of moved a little more in this sort of a fashion. We actually sent, in fact, generally just one pulse along our slinky. Now this diagram I've got here is more of a longitudinal wave. You can see a spot there where there's a bit of a rarefaction. I had moved the spring that way and created a compression that's ahead of there and a rarefaction. Tough to see, it's just a snapshot. Let's have a quick look at that. If I create a little pulse there, you can see that's a longitudinal wave. You can see the compression and the rarefaction move along there. A little bit more compressed out front, and then a little bit and just to observe our typical sort of water waves, a little bit of a combination of longitudinal and transverse. In a true water wave, particles don't just move back and forth like even a slinky. They didn't exactly do that, but it's more of a transverse wave than a longitudinal wave. The particles move. A couple of key things that we noticed in both of these cases. We haven't really discussed these yet, so let's take note of what I've written down here. Some key points about waves, about all waves. Well, first of all, we did derive the universal wave equation. Velocity is frequency times wavelength. And simply the fact that it's universal is going to mean that it applies to all waves. Now, one thing, whether it's a transverse wave where we're moving back and forth, or whether it's a longitudinal wave where we're moving parallel to the slinky, the frequency depends on the source. In either case, I am the source. In the slinky, when I created transverse waves, or in the last class, and in class we looked at the ripple tank. I'm generating the waves. I'm providing the energy. A wave is created every time I tap the ripple tank, every time I move the slinky. Okay, I am the source. You are the source when you're doing these activities. And the frequency has to be the same everywhere. Frequency, of course, is waves per second. Frequency is waves per second. It could be waves per minute, waves per hour, but in class we're going to talk about waves per second. Okay, that would be hertz when it's in per second. But either way, if I create 5 waves every second, then further on down here, they've got to continue at that same frequency. You can't create waves in the middle of nowhere, and you can't lose waves, so to speak. Energy it has to be accounted for. So every time I create a wave at one point, later on as these pass, the frequency stays the same. And the same thing goes here. I'm tapping up and down, or whatever it is that's creating the waves. Further along here, the frequency stays the same. The amplitude is kind of reflective of the amount of energy that a wave has. If I tap this harder, I get a larger crest and a larger trough, greater displacement from rest. Okay, speed depends upon the medium. Especially with a slinky, we took and we stretched this thing further and saw that the waves traveled faster, right, when this slinky was stretched somewhat. So a couple of key points that we've seen both in the slinky, in the ripple tank, and we're going to continue to see as we move through the... Okay, in the next class, we moved on and we started talking about reflection of waves. And the first thing we did was we took a look in the ripple tank and we took and reflected our circular waves off of a solid barrier. And let's take a look at how these circular waves transmit. So we had this particular ripple tank right here, or sort of a fake ripple tank, if you will. And a nice thing here is that we can pause it. Notice these circular waves are moving off in laterally in every which direction. And Okay, so here we got a ripple tank, and we could tap in here and send some circular waves towards this gray barrier on the right. So just send a couple of those things, and then we'll stop and take a look here. Okay, just send one at a time. And so here's a snapshot. I took a picture of this, and we see our circular waves. We were generating those here in the middle, and they're concentric circles heading off in every which direction. Sure how well I can draw concentric circles. You can see them better out there, but they do head out such that, you know, those arrows are tangent to the circles at each point. Okay, now they hit this wall, and you'll notice that you get a circular wave reflecting off the wall. In fact, whenever you get a crest hitting the wall, and that could be, I suppose, the dark areas there, that's when a crest is formed that's reflecting off of there. The wavelength of the reflected crest, I've made a bit of a mess of it here, is the same as the wavelength of the incident. By the way, words we're going to use, incident, that just means going towards something, and then of course reflected after it's reflected off. The reflected heading off that way. Okay, so that was the first sort of a reflected wave that we looked at. Next we tried generating some waves, straight waves. We took a different sort of a barrier, and we sent them at a barrier here, the gray barrier. I'm not sure what's happening over there in the background. Okay. But this was the next situation that we looked at. Long straight waves going directly at that barrier. Now I've taken a snapshot again of this, and here's the thing, right? Each of these dark lines represent crests. They were heading straight in. You can't even tell here if these are the ones going in or coming out. In fact, I believe they are the reflected ones. But the direction doesn't change. The speed doesn't change as I bounce off of these things. The wavelength, that's right in there, stays the same. Okay, so here what we can do is we bounce the waves off here we're at 0 degrees. There's that reflection again. Now if I put a little bit of an angle, and we actually, in the ripple tank, we changed the barrier here. We put it at an angle. Here we're sending the waves at an angle. The barrier stays straight, the gray barrier here. So I'm going to send them up from up here, and you can see those things bouncing off. Okay, maybe I'll send them from right about there, and they bounce off. Okay, so here I've taken a snapshot of that situation that we were just looking at. This is the waves reflecting obliquely at an angle. Oblique, O-B-L-I-Q-U. So obliquely. So here we've got an arrow that's kind of showing the direction that they were going towards the barrier over here. And again, we can see the waves. Okay, we actually have a word for that. We'd call it a train of waves going in here. And this would be the angle of incidence. Okay, we would label that angle of incidence. And I just managed to catch, I had a heck of a time trying to get a snapshot of this. But here's our reflected waves. I'll do them in a darker blue. Going off. Whoa, I kind of missed that. Let's try that again. Going off the barrier. Now, if you take a close look, I think that angle right there would be the reflected angle. These are pretty good at showing us the law of reflection. This arrow here is going to be showing the angle that these things are bouncing off, and you can see that the arrow between these is the same, although that's not the incident angle. I think clearly that's not the same as that angle. We're going to talk about that more later on, some of the definitions as we describe these waves. But one thing about the angle of incidence and the angle of reflection, they are always going to be the same. In fact, it's another physical law of nature, the law of reflection. States that the angle of incidence is always equal to the angle of reflection. Velocity stays the same, because the medium's not changing, they're all traveling in the same medium. Frequency stays the same. Wavelength stays the same. The only thing that changes here is direction. The only thing that's changing on these reflection. But the angle of incidence is equal to the angle of reflection. Interesting thing here, the water depth is represented here by the light blue in this area. And we've got a top view and a side view, and you can see the crests and the troughs and how the wavelength is staying the same, the velocity is the same, basically everywhere along there, whether you're looking at the top. Each of those lines corresponds with the top of the crest. If I make the water a little bit deeper on one side than on the other side, here it's deeper than it is here. Notice the speed is faster here, they slow down. A couple other things change. The wavelength changes, much closer together here, shorter wavelength here on the shallow side. Okay, and looking up here, one thing, the direction doesn't change. Right along here, light blue to dark blue, that's the boundary between deep water on the left and the shallow water on the right. So again, here's the stop action video of that. Over here is the deep, and here they were moving fast. And this is the shallow, and this is the boundary right there, the boundary between the fast and the slow, or the deep and the shallow. Okay, and you can see clearly here that the wavelength changes, gets a much shorter wavelength here, speed changes, so velocity change, wavelength change, poor writing there. Frequency, well, that can't change. That's got to stay the same. That depends on how fast you're tapping over here. You're creating the waves. Frequency has to stay the same on both sides. And finally, in this particular case, when you're going head-on from one medium to another, the direction doesn't change. The direction is the same. So next, let's take a look at going obliquely from one medium to another, from deep to shallow, from fast to slow, or something along that lines. Okay, I can't adjust this one here, but this is an image of water going from deep, and the colors are kind of different than the last one too, going from the deep section to the shallow section. And you can see here that again the wavelength is changing, the velocity is changing, frequency has to stay the same. If I'm sending in 3 waves per second, that's what's moving across over here, that's what's moving across down here. Okay, so let's take a picture of that and see what it looks like. Okay, so this is again obliquely, there's our boundary from deep, which is where waves travel faster. Same thing out in the ocean, by the way, to shallow, where they move slower. As waves approach the shore, they tend to slow down. Okay, can't say much about the amplitude here. We've seen some of that in some of the videos. The wavelength changes. Obviously, they're narrower together here. That happened when we were going head-on as well. That's boundary right there. Okay, the direction is the key thing here. So velocity changes, goes from fast to slow. They could go backwards as well. You can go from shallow to deep, of course. The wavelength changes. Pardon my very sloppy writing here. That says changes in both cases. Frequency, it's got to stay the same. Okay, that can never change. And finally, in this case, the direction changes. Okay, refraction, going from one medium to another obliquely, there is a change in direction. I was going that way, now I'm going that way. We would say this is our incident angle, and this is our, well, what we're just talking about here is refraction, so not our reflected angle, this is our refracted angle. And the angle of incidence is not equal to the angle of refraction, it is equal to the angle of reflection. Okay, that's it for that one.